Hey there, wind energy students. Dr. John Schrage here, and we've been plowing our way through learning about wind profiles in this unit. We learned about the log wind profile and the log linear wind profile. We've learned about the convective radix layer profile. And if you actually look through your book more closely, you'll see that they actually even talk about, like, for example, the power law, or which is another type of wind profile that we're not going to ask questions about on the test. There is also like these somewhat famous wind profiles that are actually classically observed wind profiles from specific locations. Again, I'm not going to ask you about, those particular wind profiles on the test. That doesn't seem particularly relevant to me. But, when you actually take these observations, that's real world, that's data, that's equipment, that's measuring, that's different from theory. Like, this is the rate it should be, or this is how it should be at night, which really opens us up to an important question. Do we actually observe any of these wind profiles? Is this actually what we see if we have a meteorological mast, or a wind profile, or launch a weather balloon? I mean, these wind profiles, like these are, I just copied this from our log wind profile lecture, and I have 3 log wind profiles under different conditions of Z0 and U star here. They look nice. They look really nice. I mean, the wind is just changing very nicely with speed of, the wind speed is changing with respect to height. There's just beautiful shape to these things. They look really nice. No, they look too nice. This looks like theory. This looks like, it's hard to imagine real wind observations at the surface are going to look anything very much like that. Because, again, using the background of this picture here as part of the story here, the real winds that are occurring are a combination of the large-scale wind, the broadly transporting air from one part of the country to another, and all of these superimposed eddies and turbulence on all these different scales, which we're going to go into incredible detail about how all that works in the 6th module, I believe it is. But, a weather station like the one I have drawn there is experiencing both at the same time. I mean, at any given moment, there's all these little random fluctuations to the wind speed that are about the passage of these little eddies. Some are big, some are small, some are clockwise, some are counterclockwise. And they're all just part of the large scale. They're embedded within the large scale flow near the surface of the Earth in the boundary layer. They're part of the story of thermal plumes rising from the surface and buoyancy and so on. And when you actually look at a data set, like this happens to be 24 hours of that Landberg data set that you can get from the textbook's website, well, you can actually see that there's all kinds of stuff going on as that one weather station was experiencing, the passage of all these little eddies and so on. And actually, keep in mind, if I just superimposed on that the large-scale conditions, and you can see, gosh, we had like an hour or so where the winds were above, and inside of that period the winds were even, there were little periods where the winds were even stronger than that. These are actually already 10-minute average winds, and we can see how there's this passage of these large-scale eddies that are part of the story of the turbulence. But actually, if we could zoom in closer and look like minute by minute or 10 seconds by 10 seconds within there, we'd see that there's all these crazy little fluctuations to the wind that we experience at the surface of the Earth as like little gusts and so on, but are really the passage of these invisible eddies and the boundaries of these plumes and so on. At any given moment, the wind doesn't really look very much at all like the large-scale wind. If we just take an instantaneous observation of the wind, what does that have to do with the wind profile? I mean, gosh, in the log wind profile lecture, we learned that if you knew the wind speed at any given height, like 2 meters above the ground at your observing station or 10 meters up on your meteorological mast, you could compute the wind at speed at any given height above the ground in the layer over which the log wind profile was appropriate. And I reproduced an equation there just to remind you about that. Does that mean that the whole wind profile is fluctuating like this? I mean, as the winds at the surface are kind of bouncing up and down as we change from, as eddies pass and so on, is the wind profile changing like that too? Well, the answer is kind of yes and kind of no. That's a little bit complicated. Now, I've got a wind, I put an antenna there. That's supposed to look like a meteorological mast on my picture here. And I'm saying, let's say there's observations, like anemometers or something, on booms at various heights along this meteorological mast. And you know what? Yes, if I had a meteorological mast like that, I would see that my wind at each of those heights, 20 meters, 40 meters, 60 meters, would also be bouncing around from one speed to another on a scale of seconds to minutes as these eddies went by and so on. So like if I actually took the winds at some particular height, let's say this is 20 meters above the ground, I'd see that they also are fluctuating. And again, let's say those are 10-minute winds. Again, if I zoomed in closer on there, I'd see, oh gosh, actually, minute by minute the winds are changing too at 20 meters. So yeah, my wind speeds at different heights are changing like that too, throughout the depth of the boundary layer. But yes and no. I mean, yes, the wind speeds are changing at different heights along the way in the boundary layer, but no, they're not changing up and down along the length of my meteorological mast in unison. Like, if the wind speeds are stronger at the surface, for the next 15 seconds, they're also stronger at 20 meters and 40 meters and 60 meters. It doesn't work that way. They're not changing in a consistent way, just trying to stay constant, consistent with the log wind profile. In fact, if I just took, I actually faked these observations in Excel just using the random number generator, but they give you an example of what I'm talking about. If that black curve was like what we are observing at the surface, well then my kind of reddish curve there would be the 20-meter wind, and it would generally be greater than the wind at the surface, and the winds at 40 meters, which are that gray curve on there, are generally greater than the winds at either the surface or at 20 meters, although not always if you look closely. And my winds at 60 meters, which are that yellowy orange curve, are even greater, although not always greater than those two. But they're not changing in lockstep with each other, like exactly when the winds at the surface are a little bit more, the winds at all those other levels are a little bit more. They're not changing in some consistent way. Not in general anyway, second by second, or minute by minute. See, the winds at all these levels are being affected by eddies at that level. As a eddy passes at the surface, there might not be a corresponding eddy, that eddy might not be 60 meters thick. A different random fluctuation in the wind speeds might be happening at 40 meters or at 60 meters or so on. The wind profile is kind of a mess at any given moment. I mean, if I just used a wind profiler or a meteorological mast to measure the wind profile, at any given instant, it would probably look something like those blue curves that I have here on this graph. The one on the left is just with a traditional XY type plot where the X-axis is wind speed and the Y-axis is height. But the one on the right there, again, has wind speed on the X-axis, but now we use a log scale on the right. This is on the Y-axis. This is a semi-log piece of paper. So those are the two representations of the same data here. Well, if I took an observation at any given moment and just said, hey, I have all these instruments up and down my meteorological tower, here's what the wind speeds look like. They look like the blue curve there. Okay. As we went up at different heights along the meteorological mast, there'd be places where the wind speeds are a little higher than we would be predicting from the log wind profile, and places where the wind speeds would be a little weaker than the log wind profile, just due to the passage of turbulence and large-scale eddies and small-scale eddies and all the crap that goes on in the boundary layer. Now, that would not be hugely different than that orange curve there, which is the log wind profile. Remember, it's that beautiful curve, graceful curve over there on a traditional XY type plot, but it makes a straight line in the semi-log graph, right? See how at every given level, it doesn't really look all that much like the log wind profile at any given moment anyway? Excuse me. We'd have to average over a period of time to make the wind profile look like these log wind profiles. And the same is true at night with a log linear profile, or during the heat of the day with a radix layer profile, or whatever. At any given moment, the wind profile doesn't look all that much like that, but averaged over a 10-minute window of time, or a 15-minute window of time, or something, we're averaging out the periods where the winds are a little stronger and a little bit weaker due to the passage of eddies. It would start looking a lot like these wind profiles. So you do need to do some averaging here to make these profiles look like this, but you don't want to average over too long of a period of a time either. Because if you took your averaging to include the periods before and after some meteorological change, like the passage of a cold front, well, what exactly would that average mean anymore? I mean, you were averaging under two very different regimes. And same with, like, you wouldn't want to have your average span, say, before and after sunset or something like that. You want your average to be on the order of a few minutes, maybe as much as an hour, but you don't want to span, like, before and after the passage of a cyclone, or span before and after a passage of a thunderstorm or something like that. Then the average doesn't mean anything coherent. Now, this time averaging then becomes an important part of our understanding of how we're going to look at data in the boundary layer, which of course is where all our wind turbines and wind technology are. Now, some of these meteorological instruments that we're going to be getting this information from are a natural fit for getting that kind of time average data. Something like a meteorological mast, or a LiDAR station, or a SODAR station, or a wind profiler. The station is, well, that's what the word means, stationary, and the air flows past it. And so you could take your location here, like with a meteorological mast, and as air flows past it, you'd be taking the average of the speeds over a period of time, maybe 10 minutes or something like that, as is the WMO standard. But it could be longer than that if you needed to or whatever. And, you know, the station stays at the same location. It is stationary. And so some of these technologies are kind of a natural fit to that. That's in contrast to, say, a weather balloon or a pieball. Now, when you launch a weather balloon, I like how I found this graph online where it showed, like, the balloon was launched at the red location there, and then you can see how the balloon went up, and they just have lines drawn down to the sub point of the balloon, so you can kind of visualize its path in 3 dimensions here a little bit. Well, the balloon is passing through the atmosphere. You can't get a 10-minute average of the winds at 40 meters above the ground from a balloon because the balloon was only passing through 40 meters on its way to some new height. And as a consequence, you only have an instantaneous value of the winds at these heights. That is a good and important theoretical consideration that, like, an atmospheric science major has to take into consideration when figuring out what to do with the data for the winds from a weather balloon, especially as we get higher up in the atmosphere. But here's the deal. Despite the fact that in the last module you actually learned all about pieballs and balloons and stuff like that, there actually is a real problem with working with weather balloons and pieballs in the lowest 100 meters, 150, 200 meters, something like that. You know, the kind of heights that, like, somebody in wind energy cares about. Because here's the deal. Modern weather balloons figure, radiosondes, the instruments hanging from the balloon on a length of string, figure out their wind speeds based on GPS technology. They figure their exact latitude and longitude at this moment, and then a few moments later they figure a new latitude and longitude, and from that they can triangulate, okay, this is how far this is how many meters we've moved over this period of seconds. Typically it's 2 seconds, by the way. And so they figure out the wind speeds from that. But there's a real problem. During the launch of the weather balloon, keep in mind that radiosonde is hanging from a few meters of string from the balloon itself. And at launch, if the wind catches the balloon a little bit, the radiosonde starts to swing from the balloon. And that displacement of, you know, possibly a few meters back and forth is a significant fraction of the total displacement of the balloon over that 2 second period or whatever. So if you let the balloon go and the radiosonde is swinging back and forth, you have a serious problem figuring out what the wind speeds are. Because the motion of the radiosonde is both the wind speed and the swinging of its position. Not to mention, of course, the errors associated with GPS technology, although that can be largely compensated for. This is a real problem. Now, as it happens, within the first maybe 10-15 seconds of the flight of the balloon, once it gets like 150, 200 meters up, this problem has largely passed, and the radiosonde is now largely not swinging. It's swinging less than the error of the GPS measurements and so on. It's not so much a problem. But in that lowest, 100 meters or so, this is actually a very big problem, and the techs who launched the balloons actually go to considerable work to be very careful not to start the balloon, the radiosonde swinging. They try very hard, especially under stormy conditions, to make sure that they will launch the balloon at a run, trying to, so that they can, they let go of the radiosonde while the balloon is going in the same direction they're running, so that they're not setting some swinging motion. But no matter what, actually, after the data come in from the weather balloon, algorithms are applied that should be able to try to correct for this, because, I mean, the pendulum motion of the radiosonde at the end of the string between the balloon and the radiosonde is a known length, and from general physics you know that there's a characteristic period to its swinging and so on, and the algorithm tries to figure out which way the radiosonde was swinging. Was it swinging in this direction or this direction? From which they can at least reduce the errors in the wind speed and wind direction that are coming from this swinging motion of the balloon. But it's actually a real problem. So down near the surface of the Earth, weather balloons have two big problems. A, the swinging motion of the balloon, and B, the fact that the balloon is just passing through the air anyway. There's no way to get like a time average. So radiosondes and weather pibals and things like that are not really the right tool for the job if we're trying to understand the wind profile near the surface. Once we get higher up in the atmosphere, that's a different story, but near the surface, this just doesn't work. Alright, I know that was kind of a breeze through, kind of a quick overview of like what observations actually tell us about these wind profiles. Let's do a couple quick questions just to kind of review what we've learned here. Question 1. Idealized wind profiles, like the log wind profile, represent what the wind profile in the boundary layer should look like. A, averaged over varying synoptic conditions. B, averaged over different times of the day. C, averaged over a period of minutes. Or D, at any given instant. What is that log wind profile actually telling us about what the wind should be looking like in the boundary layer? Make a choice from those 4 options and get a little feedback before you move on to question 2.